All right, good afternoon, everyone. So I'm happy to be here at ROSCon one more year. I've come this time to present the work that my team and I have been doing around hardware for robots, something that we've called the Hardware Robot Operating System. But before I just jump into this, let me tell you a few things of the path that led us here today. So we at Robotics, as a young robotics startup, we started producing technology in the field of drones, technology that was ROS-compatible, and that allowed people to make flying robots that were ROS-compatible and using Gazebo and all of these tools that we all love. So after a while, we started observing that our sales were doubling every second month, which was pretty cool, honestly, for us. So we kept releasing more and more tools. And while doing so, we noticed that some of the components, the hardware components, could be reused among different robots with slightly different software configurations. So that really kicked a few ideas within our team, such as, wouldn't it be great if we could have reusable components among robots with no software configuration changes needed? Wouldn't that actually simplify the construction of new robots? How about replacing damaged components with parts from different manufacturers, not just necessarily ourselves? In fact, wouldn't that actually lower the costs and knowledge required to manage robots? We thought so, and overall, we started believing that it made sense to bring ROS to the hardware level. In other words, to make components, hardware components, that were first-class participants of the ROS ecosystem. So we started asking why around. We talked to quite a few roboticists, and we found that most of them were using ROS, which is a great thing, I believe. But unfortunately, many of those actually didn't know of an equivalent for the hardware side, something that quite a few showed certain interest. Besides this, we noticed that most of the roboticists creating robots were doing so in groups, multidisciplinary groups, which were generally either a whole division within a company or a whole research lab. And surprisingly, most of their time was spent in the hardware-software interface and not in the real application that they were trying to solve with that robot. So that seemed to us quite a problem. So on the background of this slide, actually, you can see a capture from a movie. Just out of curiosity, can you raise your hands? How many people have seen this movie? Quite a few. Well, that's unexpected. It's not that good of a movie, from my opinion, especially if you're a roboticist, honestly. But truth to be told, it shows just a scene that might get your attention if you're in this field. In one of the scenes, Chappie, which is, by the way, the name of this movie, loses one of his arms. And one of the characters within the movie just grabs an arm from another robot from the ground and just plugs it into Chappie, moves it a bit around, just plugs it in, and boom, Chappie just has a new arm. It just works. I mean, no SPI, no I2C, no voltage level issues. I was freaking out. Seriously, as a roboticist, I was literally freaking out. And I'm sure many of you also did. But truth to be told, I mean, people out there that is not into robotics is exactly what they expect. I mean, they expect robots to be able to exchange parts. Actually, just think about science fiction. Haven't we seen this exact thing again and again in science fiction? Think about Star Wars. I mean, how many fans of Star Wars are here that have seen just robots exchanging parts? I've seen it myself. So what for a few might seem like just science fiction, we took it as an inspiration. And we kept digging on this concept. And the next question we asked ourselves was, is it really the right time? So if we start looking at the components that are within robot components on itself, we'll find a lot of microcontrollers, these application-specific computational units that are tiny and go from $2 up to $10. But honestly, nowadays, we have in the market computers, fully featured computers for $5 that expose I/O such as USB, HDMI, and provide much more capabilities to us, roboticists, to build robot components that are more powerful, that expose more interfaces, that are smarter in many senses. So it seemed like it's starting to be a good time to start thinking about this. So we had a look around, and we found this fantastic program called the Robotics Fast Track Program, a program funded by DARPA and supported by the OSRF Embed Systems, which looked for groundbreaking new opportunities in the robotics field. We applied, and fortunately, we got selected, so we started working on this. Just to put it clear, RFT is looking for rapid and cost-effective development with new robotic capabilities. I'm not sure if they are planning to launch another set, but I really, really encourage roboticists out there that if they have the chance, apply again, because the experience has been really, really nice so far. Anyhow, as pointed out before, that's how we officially started working in H-ROS, the Hardware Robot Operating System, which we define as a standardized software and hardware infrastructure to create reusable and reconfigurable hardware parts. In a nutshell, H-ROS is about supporting a common environment of robot components where manufacturers comply with the standard interfaces built on ROS. It's about improving the way we build robots nowadays and have future roboticists focus on those applications that will really change the world. So let me talk about a few of the things that are relevant in H-ROS and that are embedded on every single component, hardware component. So the first one is interoperability, which in a nutshell is having parts, components, able to communicate and exchange that data through ROS interfaces, in this case, seamlessly, regardless of the robot and also regardless of the manufacturer. This was critical for us. So to picture this concept a bit better, just imagine a manipulator being used in China, in industry, for example, that does a pick-and-place task. And imagine that one of the servos within this manipulator just breaks, stops working. So what should the owner of the Chinese company do? Should he just call the orange guys, possibly, and ask for a replacement or an engineer over? Or maybe he can just have a look at the market for a compatible and interoperable part and just exchange it. Wouldn't that actually save cost and time? So we believe interoperability can actually help democratizing robot components, allowing parts from different manufacturers to do the exact same job, which will impact the competitive landscape of robot components. We also looked quite a bit at the physical interface. This was quite relevant for us because we wanted to make the process of adding new hardware components to our robots as simple as possible. We looked into CAN, we looked quite a bit into industrial aspects, by the way. We looked at CAN, we looked at Ethernet, we looked at power over Ethernet, we looked at even a hybrid concept that allowed both to exchange, to communicate either Ethernet or CAN. At the very end, we ended up selecting power over Ethernet, which allows us to deliver up to 25 watts of power to every single component. Now, some of you might be wondering, yeah, sure, but I've got some components in my lab or in my industry that just require much more than 25 watts. And that's totally fine. We do support dedicated power sources within this power over Ethernet architecture of physical interfaces that we propose. Reconfigurability is actually a pretty complex topic, let me tell you that. We found quite a few groups that actually worked on this topic with results not that connected to each other. So we really wanted to attack the topic from a really humble perspective. So we started thinking, as roboticists, I'd like my robots, robot components, robots particularly, to automatically detect components that I just plug, and if possible, just use them for new applications. For example, if I just exchange the end effector on my manipulator, I just want my robot to use it. And this seems something quite complex for a roboticist, but if we ask someone out there, they're just going to ask you, are you kidding me? That's not implemented yet in your robot? And we've got that again and again and again. So we started thinking that this sort of like adding new components and ability to reuse them requires some sort of reconfiguration with our robot. So what we did, we started extending the existing URDF concept to support dynamic changes on it and recreate the internal model of the robot based on a predefined set of movements on its joints. We have quite a few prototypes that have shown quite good results with manipulators and a promising result for extending this concept to a more generic concept of a robot. Now, everything you've seen so far is based on ROS 2. So ROS, for us, and I think for many here, has defined almost the last 10 years for robot software development. And we honestly believe that ROS 2 is going to define the following 10 years. So H-ROS is betting hard on ROS 2. Now, why should I use H-ROS components when I have used components out there in the market that have ROS support or are ROS compatible? What are the differences? Well, let me point out 3 relevant ones that we believe are worth mentioning. The first one is this plug and play ability. The fact that components, as soon as they are connected, can be used. No driver installation, no issues with the ROS version, None of those. The second thing that we'd point out is that components from different manufacturers will be exchangeable. In fact, each component has its own IP and MAC addresses. It's addressable and it's accessible. So we can do many more things and expose many more possibilities with these new components. The third part that we would like to mention is this concept of smart robot components. So each H-ROS component reports additional data about itself, such as its inertial position or the power, the voltage, and the current that they are currently consuming. Now imagine the possibilities of this in a mobile robot. Imagine that each one of the components within your robot can actually report how much power it's requiring. Imagine that you could selectively turn on or off components within your robot depending on this scenario. These kind of things are things that H-ROS is going to enable. Let me quickly go through the different components that we've, the types of H-ROS components that we've created. So we classify H-ROS components in 5 types: sensing, actuation, communication, cognition, and hybrid components. Let's get into sensing components. So we know all what sensors are. They help us perceive the environment. In the H-ROS case, sensors share the information with the rest of the components in a distributed way, using standardized ROS interfaces. Examples of H-ROS sensors are rangefinders, cameras, 2D lasers, we all know sensors. H-ROS actuators will help us produce some form of physical change through common ROS interfaces. Among the H-ROS actuators, we'll find servos, brushed and brushless motors, but also things like speakers. H-ROS communication components are specialized in communication by either exposing new communication channels, for example, Wi-Fi or 4G to the whole robot, or by providing means of interconnection between different parts within a robot. So to picture this a bit better, one of the most relevant communication components within the H-ROS architecture is something we've called the backbone. So think of the H-ROS backbone as the spine of the robot that connects together all the sensors and actuators through the body of the robot and sends all that information to the brain of the robot that we've named the H-ROS cognition components. So these are specialized in computationally expensive tasks. And by the way, we don't restrict cognition components in this H-ROS architecture to be only one. We can have several brains within our robots. Something worth noting is that the cognition component within this H-ROS architecture is probably the only one that needs to be programmed, which simplifies quite a bit for many the concept of creating robots. The last but not least type of H-ROS components is the hybrid type, which basically are components composed by sub-elements, parts that contain parts and expose a general interface to comply with existing ROS abstractions. We created this hybrid type to support many of the existing robot components out there that do not quite comply with the standard H-ROS interfaces. So let me tell you a few things about the H-ROS workflow and how we expect this new trend to help when creating robots. So the first thing that you will need to do is pick your components. Regardless of the manufacturer, and as pointed out, they can come from everywhere and in the world. So the second thing you will need to do is just use ROS. We don't want you to change anything, honestly. We want you to stick with the same framework and just use all that knowledge that you already have. The third step that comes with the H-ROS philosophy is basically deploying and testing locally. And let me get into this with a bit more detail. So for any of you that are working out there with robots that use embedded components, the workflow generally is as follows. So you code your behavior with ROS, you cross-compile the code for whatever architecture your robot has, deploy the code, test and iterate again, coding back if necessary. Once you're happy with the behavior, you only have to set up those services and daemons to get everything launched. So this process takes quite a bit. We know we've done it. Probably many of you have done it as well. So with H-ROS, this distributed architecture of hardware components allows basically to simplify this whole process and have your desktop computers or your development machines act as the brain of the robot, substitute the cognition part that we've just described before within these 5 different types of components. That really helps because there's no need to cross-compile, neither to deploy constantly. So you can really iterate faster, and once you've done that, you can basically, with a single command, ship this ROS2 workspace, and seriously, it's just the ROS2 workspace which is just shipped, cross-compiled on the way, and just sent to the cognition part to the robot. So it quite simplifies the process of building robot behaviors. We're really excited about this. So of course, we didn't come empty-handed to ROSCon. We've selected the most popular robot in the ROS world, and we've turned it into an H-ROS-compatible robot. And that's how the H-ROS-Tuttlebot was actually born. So among the components included in the H-ROS-Tuttlebot, we've got a robot base, which is a hybrid component, hybrid type of H-ROS component. We've got a cognition component, which is the brain, as pointed out before. We've got a backbone, which is a communication component that helps all the components connect to each other. And we've got a variety of sensors also within the H-ROS-Tuttlebot. So due to time constraints, we actually didn't prepare a demo here, but it's actually in our booth out there. So if you actually are interested, just come out there and check some of the things that I've just explained. I mean, you can see most of the aspects just revealed here, implemented already in the H-ROS-Tuttlebot, which I think it's the first ever robot running H-ROS components. So H-ROS is now available for selected manufacturers. We have actually started quite a few conversations with different manufacturers and are really about to close several deals. In fact, many here might be surprised by this, but there's hundreds of manufacturers out there that want to get into robotics, seriously, and they don't know how to get into robotics because either they don't have the background or the knowledge, or they just don't have a fantastic software engineer, such as all of you probably, but they want to get into robotics and they don't know how. H-ROS is providing a way for all these manufacturers to jump into the ROS world. Now, while it's right now available for manufacturers, just to let you know, it'll be really soon available for the wider robotics community. If you're a hardware manufacturer, though, come talk to us right now. Now, wrapping up, when it comes to robotics, it seems like science fiction has predicted quite a bit, right? While much of it remains and will remain a science fiction, some things can actually be taken as an inspiration. We believe we are ready to bring some of those things to reality and push robotics growth and the ROS community even farther, this time into hardware. 감사합니다. Thank you. All right, questions? Hi, no, I can't.
Oh, thank you. So when I read the ROS2 design document, it raises the problem is that for the bare metal device, how to treat it as a ROS node instead of a server driver. You need to access it by the driver. So I'm wondering
I'm not understanding. Can you please start over again?
It means in your product for the components, they talking to the core part. There's a core part, right? The core.
You mean if we run ROS core?
Yeah.
Well, it's everything based on ROS2. There's actually no ROS core on ROS2.
So all the components are equal.
So basically, when it comes to, ROS2 is basically advanced in many senses. It's based on DDS, as some colleagues from the OSRF explained before. So the concept of ROS core disappears. Actually, it's a much more distributed concept. So you don't have to actually care about the previous issues with ROS1, which allows us to exactly do this.
Okay, thank you.
Okay.
I'm wondering what sort of market you're targeting, because these look like they might be somewhat research-oriented, but what about commercial applications like AGVs for factories?
So we are targeting industry for now, in the short term. Actually, we are targeting manufacturers. I think that's pretty much going to be what's going to happen in the following years or so.
But where would you think these modules would be used? What sort of applications?
So we're speaking with different industrial partners who have certain interest, certain applications where these modules can actually make sense. So in the short term, in those industrial applications. On mid-term, long-term, we actually expect that something like this actually jumps into everywhere, like from research to commercial robots. We're really excited about this, honestly. So, of course, we believe it's gonna go all around the world.
Having a dynamically discoverable node on the ROS network is a really cool thing. But when you include additional hardware into the mix, how do you secure your network when you're plugging in a new node? How do you verify that this is a trusted node, or even do any sort of security there?
So that's a great question, and to be honest, security hasn't been one of our concerns while developing this. We are still thinking about that, but we're definitely going to come with some good ideas on that. So we appreciate feedback on that sense, but as far as our existing development, we haven't been that much putting time into security.
All right, thanks.
Thanks to you.
All right, one more question. So there are many interoperability standards in robotics that I am aware of, which kind of makes each of them less powerful. So besides riding the ROS wave, where you have the choice of supporting ROS2, which is courageous, I would say, what are your plans for making the wide adoption of this standard happen, actually? Because ROS2 adoption rate is hard to predict.
So it is true that ROS2 still is in alpha, to be beta pretty soon, I believe. But to be honest, this is not something that is going to change from one day to the next one. This is something that we need to push slowly and slowly just get into people's mind that this thing is going to come to reality. As pointed out, there are many reasons why we think that this is going to become a fact. And we're slowly maturing our existing implementations, technology, and hardware backend to actually be ready when ROS actually becomes a full streamed version to align ourselves on that sense.
Thank you.
Thanks to you.